So the lecture of today will be focused on, well, first I will go through what is called gravitational time dilation, and then we will start discussing the dynamics of space-time. So up until now, we have only been discussing, well, we have been discussing the Minkowski space-time, we have been discussing the Schwarzschild space-time, but we have not yet seen where these space-times comes from. So the dynamics of why these space-times are at all interesting. So let me start now then with what is called gravitational time dilation. Now I was hoping to have time to discuss this last time, but there simply was not time. So what is called gravitational time dilation is the following. So let us have a setup. So we're going to consider now a static space-time. Now that if we look back at the lectures from last week, a static space-time is a space-time that has a time-like killing field, which does mean that we're going to be able to find coordinates such that the line element is some function alpha squared times dt squared minus some hij dxi dxj, and here alpha and hij are functions of xi only. So they are only functions of the spatial coordinates here. The time coordinate alpha and h does not depend on the time coordinate t, which means that this is indeed going to be a static space-time with a time-like killing field which is just the coordinate vector t dt. So what does this mean? Well, if we draw now a diagram of this space-time, so I'm going to draw the time axis like that, and then I'm going to draw the remaining space directions in just one line. So we have the time direction here, we have the spatial direction there. So what we're going to do is that we're going to look at stationary observers. So consider stationary observers. A and B. So this means that these observers have these static lines as essentially the flow lines of the time-like killing field as their world lines. This means in particular that if we have A here, that's the world line of A, and let's take this one, and over here is the world line of B. So this is B and this is A. So they have fixed x coordinates, whereas the time coordinate changes. Now, since we don't know exactly what these functions are, we don't know a priori how the light-like geodesics look in this space-time. However, what we do know is that if I take a light-like geodesic now going from A to B, I know that due to the time translation symmetry, if I translate this geodesic in time, I'm going to get a new geodesic. So it's going to look something like this. So both of these are geodesics. If this is a geodesic, then its time translation is also going to be a geodesic. This is because of the symmetry of the space-time. So that means, of course, that this coordinate distance, you can call it T0, it's going to be the same coordinate distance as this one, because all we have done is a time translation here. And then we can ask the question, how much time does A experience between those two events, and compare that to the time that B experiences between those two events. So we can do a simple calculation here. So what we get if we're going to write down the proper time of A, well, if we call this time, well, TA, then this time is TA plus T0. So this proper time is going to be given by the length of the world line between those two events. And since we can parameterize the world line just with the t parameter, what we find is that this between those two events is equal to the integral from TA to TA plus T0, and then the square root of the metric acting on this time-like vector field integrated with respect to dt. And assuming now that alpha here is a positive function, it's also constant since it doesn't depend on t. It's a constant along this world line. So I can just take that out, and we get alpha evaluated at the point A, multiplied by the integral of dt from TA plus T0, which is of course just alpha A multiplied by T0. So this is the proper time elapsed for observer A between those 2 points. We can do the same argument here for the B observer, just taking instead this time to be TB and this time to be TB plus T0. So the proper time for B in the same fashion is going to be alpha B multiplied by T0. So of course now both of those proper times include the variable T0, which means that if I take the ratio of those two, if I take the proper time elapsed for the B observer, divide that by the proper time elapsed for the A observer, this is going to be equal to alpha B divided by alpha A. So it's only going to be dependent on this function that multiplies the t coordinate in the line element. So this means that if alpha B is larger than alpha A, then for the same change in the global time coordinate, B will experience a longer proper time. So the prime example of this we find in the Schwarzschild metric. So for the Schwarzschild metric, we remember that from last time that the Schwarzschild metric is 1 minus rs over r dt squared minus 1 minus rs over r to the power minus 1 the r squared minus r squared d omega squared. Now we have exactly a static spacetime here because this function 1 minus rs over r is exactly this alpha function that we had before. So we or rather the square root of that, whereas here we have some metric components multiplied by the spatial coordinates. So in the end, these just depend on the spatial coordinates, and these factors only depend on the spatial coordinates. So we have exactly this static spacetime. So if we take an observer at spatial infinity, so we let r go to infinity and compare that to a stationary observer in a gravitational well at r equal to r0. So we can call this observer A and this second observer B. So that means that the time elapsed for the distant observer divided by the time elapsed for the observer inside the gravity well, that's going to be here 1 minus rs divided by r. But for the A observer, we take the limit as r goes to infinity. And for the B observer, I guess there's a square root here as well, because it was alpha and not alpha squared. We have 1 minus rs divided by r0 to the power of 1/2. So, of course, now the this in the limit of r going to infinity is 1. So what we end up with here is 1 minus rs over r0 to the power of minus 1/2. So since this now minus rs divided by r0, this is smaller than 0, which means that this number is going to be smaller than 1. So when we take the square root, we still get something smaller than 1. And when we take it, when we take 1 divided by that, we get something that is larger than 1. So this means that a longer time is going to pass for the observer between the same time coordinate for the observer at infinity compared to the observer inside the gravity well. With that said, let's also look at gravitational, because it's related, right? So gravitational redshift. So I'm just going to copy now this image that we drew here, at least the important parts. So we have this situation again. This is not really important at the moment. So the question now is, if these two light signals here represent the wave crests of, well, successive wave crests in a light signal that is sent from A to B, so then this T0 that we had here, this would be the period of the wave observed by A, and likewise, well, the proper time here, so tau A. And here tau B, the time, proper time experience between the wave crest for the B observer, would be the period of that wave for the B observer. However, the frequencies are inversely proportional to the proper times experienced between wave crests. So that means that if we take the frequency observed by A and divide that by the frequency observed by B, then what we find is that this is going to be equal to tau B divided by tau A, which we already found that this was alpha B divided by alpha A. So if we look now back at the Schwarzschild metric, we find that if this observer inside the gravity well sends a light signal out to the observer at infinity, that signal is going to be redshifted. So the frequency is going to go down in that case. I mean, this can also be argued in the same way as we argued regarding frequency shifts in general. This is just a kind of a similar, a simpler argument for this particular case. But let's move now on to the next topic, which is the dynamics of spacetime. So the question now is that before today, we've always been considering spacetimes that have been given to us, the Minkowski spacetime or the Schwarzschild spacetime. We had the de Sitter spacetime as an example at some point. But we now come to how will we actually determine what metric we should be using. And this is similar kind of to Newtonian mechanics or in electrodynamics. In electrodynamics, you have the equations of motion for how a charged particle moves in an electric field. But without the Maxwell equations, you don't a priori know what this electric field should be. So this is kind of the same. So far, we have been discussing how a test particle would move in a given spacetime, but now we need to know what this spacetime is. So what is the metric? So let me just go back to the correct place in my lecture notes. So the way to do this is to find some way of deriving, just as we have derived the Maxwell's equations as the field equations of electromagnetism, we need to derive what is called the Einstein equations as the equations of motions for the metric. So in order to do this in electromagnetism, what we do is that we write down a Lagrangian, and based on that Lagrangian, we vary the action, and we arrive at the Maxwell equations essentially. So the way to do this in general relativity is that we write down what is called the Einstein-Hilbert action. Now, this can be argued for in several ways, but for our purposes, I'm just going to write down what it is. So we're going to have some normalizing mass scale here, squared, divided by 2. And then we're going to have a integral over all of spacetime, because our action should be an action over all of spacetime. And then we need some integrand here. And since we are integrating over all of spacetime, what we should have here is something like a volume element of spacetime, and then some kind of Lagrangian multiplying that volume element. So I'm going to erase this now. I'm just going to say that, and then we're going to see what we're having. So the Lagrangian a priori is a scalar, and since we are going to describe the metric, this scalar better be dependent somehow on the metric. And kind of the easiest scalar that we can write down, based on everything that we have done mathematically so far, that kind of describes the curvature of this spacetime, is the Ricci scalar. So I'm going to just write down the absolutely easiest scalar I can think of based on this framework of differential geometry that we discussed, which is the Ricci scalar. And then I'm going to multiply by the general volume element here. And one can convince oneself that if I want to have a volume element in general coordinates and I have a metric, the natural volume element is to take the square root of the determinant of the metric and multiply that by the differentials of the coordinates. So I have here a minus sign because the determinant here of the metric, let me just write that down, G is the determinant of the metric, is going to be negative, since I have a signature which is plus, minus, 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 3 minus signs, so the determinant is negative. In order to take the square root of that, I need something positive. So this is kind of the absolutely simplest action that I can write down, and it's called the Einstein-Hilbert action. So being given this Einstein-Hilbert action, yeah, so let me say that also. This MPL here is going to be equal, well, squared is 1/8 pi times Newton's gravitational constant g. So this is the Planck mass. Right. So now this action, the Einstein-Hilbert action, it contains up to second-order derivatives of the metric itself. So what we can do now is that we follow the same procedure that we usually do in classical mechanics, where we have the action. So in order to derive the field equations of something, we need to vary this action with respect to this. Sorry. So let me just multiply everything by -16 pi g, and then multiply by the variation of the Einstein-Hilbert action in such a way that all I have left is this integral. So I have this integral left, and then I have two terms in the integral, which a priori I'm going to vary, which means that I can just apply the product rule. So I get here the variation of the Ricci scalar multiplied by the square root of the determinant of the metric, plus another term where I have the Ricci scalar and I multiply it by the variation, the square root of minus g. And then the same thing, d4x. So the question is, what am I going to vary with respect to here? So the easiest thing, it turns out, is that we're going to have the variation with respect to the inverse metric components. So I want to write everything in terms of how I would vary the inverse metric components. Now this is of course the same thing as varying the metric components, just in a different basis. But for our purposes, it will be easier to vary the inverse components of the metric. So let me now introduce, let me call this term 1, and let me call this term 2. So if I look at term 1, so this would be the variation of the square root of this metric. In order to find out what this is, I'm going to look at the following. So I'm going to make a trick, which is to look at the Kronecker delta. So I take delta AB, and I'm going to write that as the product of the metric and the inverse metric tensor. So GAC, GCB. Now, the components of the Kronecker delta are constants. So if I vary here the left-hand side, I get 0. Whereas if I vary the right-hand side, I get something like GCB delta GAC plus GAC delta GCB, right? And so this should be equal to 0. So this is something that I will use later on. We also know, so this is a matrix identity. In general, that if I have the trace of the logarithm of a matrix, then this can be rewritten as the logarithm of the determinant of that matrix. So I'm going to use this for the matrix representation of the metric. So I'm going to put A equal to G here. And then we're going to see what this is. So I'm going to vary this. So I'm going to take the variation of the trace of the logarithm of the metric G. Now this is, since the trace is linear, I can enter the variation inside here. So I get the trace of the variation of the logarithm of G. But this is going to be equal to the trace of G inverse and the variation of G. Now this is just ordinary differentiation rules that are applied here. Now in components, this is going to be written as G AC delta G AC, because we took the trace here, or CA, but the, I mean, a priori here CA, but the metric is symmetric. So comparing this now to what we had here, we have the logarithm of the, sorry, we should have here delta of the logarithm of the determinant of G. So this is just applying this matrix identity. But the determinant of G here, that's just a function. So we find that this is equal to 1 over the determinant of G times delta G bar. So if we bring everything together now, we have delta G bar here, and when we differentiate this, we're going to get something which is delta G bar. It's going to have a 1/2, and it's going to have a minus sign in it as well because of the minus sign here, and so on. But we're going to get something that depends on delta G bar. But here we have an expression for delta G bar in terms of the variation of the metric, which we, using this formula, can express in terms of the variation of the inverse metric. So I'm not going to go through the exact computations, but you can find them in the lecture notes. What we find in the end is that this, the variation of the square root of the determinant of the metric, is going to be equal to minus 1/2 times the square root of the metric, or the determinant of the metric, G mu nu delta G mu nu. So this is the final form for the term here that we were interested in, which is going to, we're going to insert it here in the variation of the action. So there remains the second term, so where we had the variation of the Ricci scalar. But if we just insert what the Ricci scalar is, it's the variation of G mu nu R mu nu, which we're going to be able to write as R mu nu delta G mu nu, which is already on the correct form, with expressed in terms of the variation of the inverse component of the components of the inverse metric, plus G mu nu, and then the variation of the components of the Ricci tensor. Now, I don't really have time to go through the exact computation here either, unfortunately, but it is already in the lecture notes. And the base thing is to consider now that, so consider that if you have two different connections, so the Levi-Civita connections of two different metrics, so this would be the kind of the variation of this expression, then this is going to be a tensor. That's the basic idea behind this. So that means that the variation of the Christoffel symbols are going to be the components of the tensor, of a tensor. And once we have that, we can go through everything And what we're going to find is that G mu nu delta R mu nu, we're going to be able to write this as a total derivative of something, where this something is there. So this means that this term in the variation is going to be a total derivative, so it's not going to affect the Euler-Lagrange equations. So we're going to be able to disregard this term when we are deriving the Euler-Lagrange equations for the metric. So not important for the Euler-Lagrange equations. So what this means is that we end up with minus 16 pi g times the variation of the Einstein-Hilbert action is equal to this integral. And then we have R mu nu coming from this term minus 1/2 g mu nu times the Ricci scalar, and then we take the square root of the metric determinant outside of that and integrate with respect to the coordinates. And if we want this to be equal to 0, so we want the variation of the Einstein-Hilbert action to be 0 for all variations of the metric. Sorry, I missed here the variation of the metric. Please stop me when I do silly things. So we have here delta G mu nu, the variation of the inverse metric components. So this could be anything. So in order for this to be 0 when this is arbitrary, then whatever is in this parenthesis must be 0. And if you remember back a few lectures, this was what we called the Einstein tensor, G mu nu. So the field equations corresponding to the Einstein-Hilbert action are exactly this. So R mu nu minus 1/2 G mu nu Ricci scalar equal to 0. And this is known as the Einstein field equations. In vacuum, because so far we have not introduced any other matter fields into this. So these are the Einstein field equations in vacuum, which also means that there's a 0 on the right-hand side here. So this is, for example, the equations that the Schwarzschild metric is going to satisfy, because it's a vacuum solution to Einstein's equation. So it's 2 o'clock. Are there any questions on what we've done so far? Okay, it's 1/4 past, so let's continue. So what we did the previous hour was to discuss the Einstein field equations in vacuum. However, in many cases, we are not going to be in vacuum. And well, for example, in the Minkowski space is a solution to these field equations here, because it's rather easy to verify, because if you put Minkowski space in here, well, the curvature is 0, so the Ricci tensor is 0, and the Ricci scalar is 0, so 0 is equal to 0, and Minkowski space is a solution. As I also said, Schwarzschild metric also a solution to this. However, if we start including matter, it becomes slightly different. So what I'm going to do this hour is to including matter fields. So in general, this is going to be that we add some new field that describes how matter works, or some content into our space-time. Now this can be, for example, For example, the electromagnetic field. If I include the electromagnetic field in this, how are the Einstein equations going to change? One can ask that question. So it's the question of what essentially happens when I don't only have the geometry of spacetime itself, but I also include some additional fields in the spacetime. So in the presence of additional fields, so this would be some fields defined on spacetime, so they're going to be essentially functions of the coordinates. Then we need to add the action corresponding to those fields. So the total action, S, is going to be the Einstein-Hilbert action plus some additional action, which we are going to just put matter as the subindex. So we're going to have the Einstein-Hilbert action plus something that is the integral over all of spacetime, and I will write it now schematically in the same way that I wrote the Einstein-Hilbert action in the beginning. I'm going to have some Lagrangian, well, actually Lagrangian density, that is a scalar field that depends on the fields that we have entered. And then we have this volume element, the same volume element as before, so minus, so the square root of the metric determinant, and then the integration with respect to the space-time coordinates. So L here is the Lagrangian density. So the thing here is that I no longer want to vary the Einstein-Hilbert action and put the variation of that to 0. What I instead want to do is that I want to vary the total action and put that to 0. So if I put the variation of the total action to 0, that means that the variation of the Einstein-Hilbert action, that must be equal to minus the variation of the matter action. Now, we know what's on the left-hand side here. We computed it last hour. So in essence, we had the variation of the Einstein-Hilbert action. It's minus 1 over 16 pi g multiplied by the square root of the metric determinant, and then this Einstein tensor. So we know that part already. The question is, what is the variation of the matter action with respect to the inverse of the metric? We don't know that a priori. We don't know that unless we look at the variation now of this part with respect to the inverse metric. So I'm going to leave that as is. But what we do find out, so when we do all of this variation, what we find out is the following. If I take now minus, let me put it like this. So if I solve for the same thing as we had before the break, so the Einstein tensor here, since this is a part of the variation of the Einstein-Hilbert action here, I can just solve for this part. What I'm going to find is that this is going to be equal to some tensor t mu nu, which is going to be given by 8 pi g. No, sorry, the 8 pi g should be here. This is 8 pi g times t mu nu. So this is the definition rather of t mu nu. So once we have solved for everything, t mu nu that's going to be equal to 2 divided by the square root of the metric determinant, and then the functional derivative of the matter action with respect to the inverse components of the metric. So this is what we're going to call the energy momentum tensor. And if you look at these Einstein equations, these are the Einstein equations, well, the general Einstein equations, Einstein field equations. So we're no longer in vacuum. If we were in vacuum, this right-hand side would be 0. But we're no longer in a vacuum, so in general, this is going to be the form of the energy momentum tensor. And since we have a lot of derivatives of the metric here, what this is actually doing, it's acting like a source term for this equation, for this differential equation. So if we put in some fields here that are non-zero, giving a non-zero energy momentum tensor, then Minkowski space, for example, is no longer going to be a solution here. So in general, if you add something to your spacetime, you're going to have a different solution. And that's described then by these Einstein field equations. Now, it can be rather tricky to solve this, because many times, in order to interpret what you have, what the things inside this this energy momentum tensor actually mean, you need the metric in order to interpret it. But you don't know what the metric is until you have solved this. So it can be rather tricky to actually solve this analytically in the case where you don't have something that's a rather simplified situation. Any questions so far? Okay, so let me take an example here. Examples always work great. So let us take the example of the electromagnetic field. So for the electromagnetic field, the Lagrangian density, you may recognize it. It's given by the field tensor, and it's minus 1/4 f mu nu f mu nu. But I now want to write this in terms of the field tensor with only the lowered indices, because f mu nu here, you might or might not know, is d mu a nu minus d nu a mu, where a here is the 4 potential of the electromagnetic field. And since in order to write something like this, I would need to raise the indices with the inverse metric. And I also want to vary then later with respect to this field. So I can rewrite this as minus 1/4 f mu nu g mu sigma g nu lambda f sigma lambda. So that's just writing everything now in terms of the inverse metric components and this electromagnetic field tensor. And this electromagnetic field tensor now does not depend, with the indices lower, does not depend on the metric. So when we make the variation of these two with respect to the inverse of the metric, we're going to get 0. So with that, we can take the variation now of the electromagnetic action, which is, again, you take the Lagrangian density and you integrate over space-time. So going through this, it's again a rather lengthy computation, but what you end up with is something like the follows: -1/2, and then we have G mu sigma, F mu nu, F sigma rho, delta G nu rho, plus G mu sigma, G nu rho, delta F sigma rho times F mu nu. So this is just varying each term individually. Minus, and then we have a term which is the Lagrangian itself, and delta square root of minus G bar d4x, and this of course also goes here outside of everything. So minus determinant of G d4x. Now, as we said, this thing here does not depend on the metric components, so that is equal to 0 when we vary with respect to the inverse metric. However, here we have the inverse metric, and this thing we already computed when we computed the variation of the Einstein-Hilbert action. So if we go on here, and when the smoke settles, we're going to find that the derivative of the electromagnetic action with respect to the inverse metric components is going to be -1/2 F mu nu F mu rho. Now I have mixed up the indices with what I had in my lecture notes. So let me rectify that. It was nu rho here. So we have three indices, nu and rho on the left-hand side and nu and rho on the right-hand side, minus 1/4 G nu rho F alpha beta F alpha beta. And all of this multiplied by the square root of the metric determinant. Now, if we compare this to the definition here of the energy momentum tensor, we find that the energy momentum tensor, that's going to be minus F mu, again, indexes. I want nu rho here, F mu rho, plus 1/4 G nu rho, and then this F alpha beta, F alpha beta. Now, I'm not sure if those of you taking special relativity now have reached this point that when you consider the energy momentum tensor of the electromagnetic field. But if we look at this, it's exactly what you would expect if you consider the 0,0 component to be the energy density of the electromagnetic field, the mixed time spatial parts, the Poynting vector, and essentially the space parts, the electromagnetic stress tensor. So this is actually exactly what we would expect. From special relativity and EM fields. So we can arrive at this from that direction as well. So this would be kind of the way of deriving the Einstein field equations when we include the electromagnetic field. Then you would have to include this stress energy or energy momentum tensor on the right-hand side of the Einstein field equations. However, this does not tell us how the electromagnetic field itself behaves. In order to do that, we would have to take this variation of the electromagnetic field action, and we would have to vary it with respect to this 4 potential instead. And if we did that, then we would end up essentially with with Maxwell's equations in a curved spacetime. So that would essentially be putting the metric terms to 0 and instead having these terms non-zero. However, when we derive the stress energy tensor or energy momentum tensor, then this term was 0 because we were varying with respect to the metric. Any questions so far? Okay, so what we've been discussing now was essentially, it was a part of both courses. I'm now going to go into a bit more detail about the stress energy tensor, or as I already called it several times, also the energy momentum tensor or the stress energy tensor, kind of interchangeably. If you like something, it has several names. But this part that I'm going to discuss for the rest of the lecture, a priori is, so this is going to be a bit deeper discussion on this stress energy tensor. Is only going to be part of the larger course, the SH course. Of course, if you're taking the SI course, you're more than welcome to stay. So we're going to now discuss the stress energy tensor. Or the energy momentum tensor. If you wanted to be very, very particular, you would probably say stress energy momentum tensor, because the interpretation, if you go to Minkowski coordinate in special relativity, for example, is exactly that we have one term which is the energy, one term which is the momentum density, and one term which is the stresses in a material. So the question now is, what is this? What is T mu nu? And this is what we're going to try to answer here. So if we look at the Einstein equations, we had essentially that G mu nu was 8 pi G multiplied by T mu nu, where G mu nu here was this Einstein tensor. So G mu nu is equal to the Ricci tensor minus 1/2 G mu nu multiplied by the Ricci scalar. So this thing here that is on the left-hand side, it only depends on the metric, and the connection only depends on the metric. So in particular, we can compute the divergence here of G mu nu. So I raised the indices and I computed the divergence here, which is taking the covariant derivative and contracting two of the indices. And if you do this computation, it turns out that this is 0. Always. As long as you have the Levi-Civita connection, this is 0. But this means that also, if you do the same thing on the right-hand side, that the divergence of the stress energy tensor should be 0. So this corresponds to conservation law. And the reason I'm saying that is that, let's take an example here. So example, look at Minkowski space. Or you don't really need to look at Minkowski space. You can just look at local coordinates where the Christoffel symbols vanish. So you have one time direction, you have three spatial directions, and the Christoffel symbols vanish. So gamma ABC equal to 0 essentially. And what the form that this then takes is the following. So we get d mu t mu nu. I can write out the sum here and I can split it into the spatial components and the temporal components. That means that I could write this first as d0 t0 nu plus di ti nu. So I here runs from 1 to 3, and 0 here is corresponding to our time variable. And this should be equal to 0. Now this is very reminiscent of something. This is very reminiscent to if I would say that this thing, which is here, so this is a component of, for each fixed nu, this is a component of something. Well, it's a component of the stress energy tensor, but I can call it rho nu. And this thing, I can call it the I components of some vector j nu. If I do this, then what this is saying is that d rho nu dt plus the gradient of j nu is equal to 0. And this is the continuity equation. It's the continuity equation without the source, which means that something here is conserved. So this is corresponding to a conservation law. And that's why I'm saying that it is. If we look back at the example of electromagnetic fields, so for EM fields, T00 would be equal to 1/2 epsilon 0 E squared plus 1/mu0 B squared, which you may or may not recognize from electrodynamics as the energy density of the electromagnetic field. We would also have that T I0, this would be the I component of 1/mu0 E cross B. So the I component of that, well, that's the pointing vector. It's the I component of the pointing vector. So what would be the density here for nu equals to 0 would be the energy density of the electromagnetic field. And the corresponding current would be the pointing vector. The remaining 3 with nu equal to 1, 2, 3, well, then the pointing vector would be the density essentially. And we also know that the pointing vector describes the momentum density of the electromagnetic field. And what we would get here would be the components of the stress tensor, which is then the current of momentum in the electric field. Any questions regarding that? Okay, so just to take another example, we can look at the point particle. So look at the point particle in a Minkowski background, essentially. So the action of that point particle would be defined as the mass of the particle multiplied by its proper time, which is g mu nu x dot mu x dot nu, and then integrated with respect to the curve parameter. Now, this is not an integral over all of space-time. This is just an integral along the world line itself, because the only parameter here is the curve parameter. However, using a delta function, a three-dimensional delta function on space-time, this can be rewritten as an integral over space-time. And when we do that, what we would find is that this energy momentum tensor would be given by m x dot mu x dot nu, and then this three-dimensional delta function, which is essentially x minus x of t, where this x of t is now the path that the particle follows, and this x here is the position in space-time. So one thing that we can see then is that the energy momentum tensor of a point particle is going to be non-zero only along the world line of this particle. And if we actually go and look at what the different components are, if we look at, for example, T00, that's going to be the mass multiplied by essentially this three-dimensional delta function, which is in essence going to be the energy density. And similarly, if we look at Ti0, that's going to be essentially m, then the I components of the velocity, and this same delta function, x minus x of t. So again, this would be momentum density. I'm now looking at a slow-moving particle, it should be noted. Okay, so that about that. So this is kind of motivating for us to see why this tensor that a priori appeared here in some strange form when we were varying the total action with respect to the metric, why we can actually interpret this as the energy and momentum densities of the corresponding matter fields. The last thing I want to do today is to discuss something called ideal fluids. So this is a particular type of matter content in a space-time, if you will. So it is an ideal fluid is something that can be described to have energy momentum tensor which can be written on the following form. So T mu nu equal to rho 0 plus some capital P u mu u nu, actually it should be a small p, use the same, minus p g mu nu, where here now u mu is the components of the forward velocity of the rest frame of the fluid. Rho zero is the energy density in this rest frame, and P is the pressure. So an ideal fluid, that's something that can be described by these three things: the rest frame of the fluid, an energy density in that rest frame, and a pressure in that rest frame. So, for example, if you go to Minkowski space, in Minkowski space, you would have something as follows. You would have that T mu nu would be rho zero plus P u mu u nu minus P eta mu nu, because in Minkowski space we have the Minkowski metric. And if we then look at the rest frame, that is, we put u mu equal to 1, 0 mu. So we look at the rest frame of this fluid, then this would be given by the mu nu components of rho zero, and then zeros on the off diagonals. And then we would have, let's see, we would have P here in the spatial components. So that would mean that the energy density in this rest frame indeed would be rho zero. The stress tensor would be directly given by the pressure, with the pressure on the diagonal. And in the rest frame, of course, we also have no momentum. So the time space mixed components will be 0. So that kind of motivates why we would call this an ideal fluid, and the interpretation of rho zero as the energy density in the rest frame of the fluid, and P as the pressure. So with that said, I just want to also make it reasonable to you that we have a few different cases in if we have a particle gas. So if we have a particle gas, we should have some form of the energy momentum tensor of this particle gas. So what we're going to consider now is that we have some distribution. We have some particle gas consists of particles with some distribution function in momentum. So consider an ensemble of particles with distribution function f of p. So this means that that if I have an extensive quantity with spatial density, is given by A, then it will take the form that A is going to be the integral over all momenta. So the integral over all momenta, f of p, and then A of p, where this A of p, sorry, or A of p is the addition to A of a particle with momentum p. So if we now want to look at the energy density of these particles, it's going to be given as follows. I'm going to call it E now. That's the integral. And if I have a particle with rest mass m, and it's moving with some momentum p, that's going to give an additional gamma factor to the energy of that particle. So when I'm looking at energy as my extensive quantity, then the energy of a particle with momentum p, well, it's mass multiplied by the gamma factor. And the gamma factor can be computed from p and the mass, because given that we can compute the velocity itself. And then f of p d3p. Now, if I go to spherical coordinates in momentum space, I can re-express this as 4 pi, and performing, of course, the angular integrals. And I integrate from 0 to infinity, so I integrate over all momenta, and the energy is m squared plus p squared. Then we have a p squared from going to spherical coordinates, f of p dp. If I look at the momentum density, so this is capital Pi. It's something similar. It's Pi, the momentum component, f of p d3p, but this is going to be 0, assuming that I'm looking at a distribution function which is spherically symmetric, because this Pi here is, of course, an odd function of p. Finally, if I look at the stress, it's sigma ij. It's going to be given by pi pj divided by square root m squared plus p squared f of p d3p. So again, if we look here, if I is different from j, we again here have something that's odd in pj, so integrates to 0. However, if I is equal to j, we're going to find out something different. And what we're going to find out is, well, let me write that on a separate line. So the rotational symmetry actually tells us that it doesn't matter here. So if this is rotationally symmetric, it doesn't matter if I put I and j equal to 1 or I put them both equal to 2. So we can actually conclude here that sigma ij, that's going to be some p multiplied by the Kronecker delta ij. And we can now find this p by taking the trace here. So what we compute is sigma ii, which is then going to be 3p, which we can compute. And what we will find out is that this is 4 pi over 3. Then the integral from 0 to infinity, p to the power of 4 divided by m squared plus p squared, f of p dp. Again, we have used the spherical symmetry to perform the integral over the coordinates here. Sorry, there should not be an equality sign here. Let me do the following. So what I should have here, I'm of course solving for P here, which is leading to why I get this 3 in the denominator. So this gives us essentially the fact that if we look now, let me draw this here because it will actually fit here. If we look at the energy momentum tensor, so T mu nu, we know that it should contain the energy density there. It should contain the momentum densities here and here, and it should contain the stresses in the space parts. So this is now actually the energy density, zeros in the off diagonals, because in as long as F here was rotation symmetric, we had zero momentum, and then we have these P's here. So this is exactly an ideal fluid. So as long as we have a particle gas with some distribution function that is rotationally symmetric, we do end up with exactly what we would have for an ideal fluid, with some energy density and some pressure. Now, in the last 2 minutes, I want to discuss 2 special cases here. So I want to first discuss the case where m goes to 0. So that would correspond to a distribution of massless particles. Equivalently, we could consider the case where F is such that we only have particles of much higher momentum than the mass itself. So in the limit of P squared much larger than m squared, then if we look at the energy here, this factor is going to be approximated by P. So we would have the integral of P to the 3rd power f of P dP. So this would be 4 pi integral P to the 3rd power f of P dP. However, for the pressure, we could do something similar, except now we have this this expression in the downstairs, but we still get P to the power of 3 here, and a prefactor of 4 pi over 3. So we would have 4 pi over 3 P cube f of P dP, which would be equal to 1/3 of the energy density. So for a highly relativistic gas, we would have that the pressure is 1/3 of the energy density. And we're going to use this later on when we're looking at cosmology. So we're going to fill the universe with, for example, a photon gas, which would be this highly relativistic gas. But we also have a different case, and it's when we have the opposite. So when m squared is much larger than p squared, which would correspond to our particles not having an energy which is sufficient to make it relativistic. In that case, all of these square roots would be approximated by m instead. And we would end up with something that the energy density instead is much larger than the pressure. So that would mean that we could approximate the pressure of being approximately 0. And then we would still have an energy density, but the stresses in that case would be approximately 0. And this is called essentially dust. So this is what we call it. It's essentially a gas of non-moving particles, or of non-relativistic particles, whereas this is a relativistic gas. for example, a photon gas. It's 1 minute past. I have finished what I wanted to say today.